So last time you've seen how to add 2 points on an elliptic curve graphically. Let's now do this algebraically. Actually, let's compute the coordinates of the sum of the points given the coordinates of the 2 points. So let's start with the picture again. So here's the xy coordinates. And we'll take an elliptic curve that looks like this. Okay, so that'll be our E, and we'll give it an equation. Y squared equals x cubed plus ax squared plus bx plus c, where a, b, and c are real numbers. It's a smooth curve. No sharp corners. And let's take 2 points on it. Let's call them P and Q. So the point P, whose coordinates will be x, p, y, p. And another point, let's say here, Q. Its coordinates will be x, q, y, q. All right, so then to find the sum, I connect them by a line. As you well know, the line intersects the curve at yet another point. So here, so I'll call this point R, XR, YR, and if I flip it here, with respect to the x-axis, I get the sum. So this point here is P plus Q. That's what we want. So this is xp. Sorry, xp plus q. yp plus q. Okay, so this situation is, of course, actually it's not very special. It's like the generic situation you may encounter. But there are some special situations which this picture doesn't cover. So let's just quickly take care of these special situations right away so we don't have to come back to them and derive the formula for this non-special situation. So special cases first. So first of all, there are 2 possibilities, right? You can have P equal to Q or P not equal to Q. Here on this picture, P is not equal to Q. It's not the same point. I'm not trying to compute 2P. I'm trying to do P plus Q, where P and Q are different points. But there are some special cases. So one is when one of these points, say P is equal to infinity. Well then, P plus Q is Q. Remember, P, the point P at infinity, works as 0 for this new type of addition. So 0 plus anything is that anything. That also covers, right, covers also so a special situation where both points are equal to infinity. 0 plus 0 is 0. Okay, so that's one case. So from now on we can assume that none of these points is equal to infinity. So another situation is when P is equal to negative Q. So that means that the points are stacked on top of each other, right? Because remember, if this is my point P, then the exact reflection of it with respect to the x-axis is negative P. So when the points are just negatives of each other, so this happens, i.e. if xp is equal to xq, so they have the same x coordinate when p is not equal to q, or when p is q, that means the point is here on the x-axis. Or if yp is 0 when p is equal to q, in both cases the sum is equal to infinity, right? Because p plus, so if p is negative q, then I get negative q plus q, that's 0. 0 for this addition, so infinity. So if one of the points is infinity, or if they're stacked on top of each other, or if I'm trying to double a point when the point lies on the x-axis, then the answer is always infinity. So these are the special cases, right? So now we can assume, that neither p nor q is equal to infinity. So there are actually physical points on this plane. And so there are two cases. If p is not equal to q, that xp is not equal to xq. Or if p is equal to q, we can assume that yp is not 0. Alright, because of these other situations were covered by these special cases. Okay, so these are our assumptions. So we're first going to go after the assumption that p is not equal to q. So first, p is not equal to q. None of them are infinity. None of them are equal to infinity. And xp is not equal to xq. Because xp is not equal to xq, so they're not on top of each other, there's the line that connects, the secant line that connects p and q has a well-defined slope. So this implies that the line L through p and q is of the form L equal to, so y equals lambda x plus mu. So lambda and mu are some real numbers. Okay, so that's the L. So the picture was already for that non-special situation, for none of these special cases. And in fact, right, we can compute what this lambda is. Lambda is equal to yq minus yp over xq minus xp. Right, you see where I'm using the assumption that xp is not equal to xq, because I'm dividing by the difference, so I don't want the difference to be 0. All right, so I have the slope of this line. So now we want to compute these points, right? These coordinates here. And it's enough, you see, it's enough to just compute xr and yr, because the first thing here we want to note is this. Note xp plus q is equal to xr. After all, these points are exactly reflections with respect to the x-axis, so they have the same x-coordinate. On the other hand, what about the y-coordinates? Well, they're negatives of each other. So yp plus q is equal to negative yr. Okay, so that means I really have to just find the coordinates of the third point of intersection, and then I will know the coordinates of p plus q. So let's do that. So how do we do this? Well, how do you, again, find points of intersection between a line and a curve? You just equate them. So just like we did before, we take this, right, and we square the y. So we have that y squared is equal to lambda squared x squared plus 2 lambda mu x plus mu squared. Okay, and now we set these two equal to each other. So this and that. So we got x cubed plus ax squared. Let's just write it like this. X cubed plus ax squared plus bx plus c equal to lambda squared x squared plus 2 lambda mu x plus mu squared. Okay, and as before, taking everything to one side, we get a cubic equation. So we got x cubed plus a minus lambda squared x squared plus b minus 2 lambda mu x plus c minus mu squared equal to 0. So the x coordinates of P, Q, R are the roots of this equation of f of x. So I call this f of x. So how do I find them? Well, I just need to solve this cubic equation, right? Well, solving cubic equations is difficult, but I can actually do something different. Namely, I know already two of these roots, right? I mean, P and Q are points that are given to me. So I know xp and I know xq. So if I know two roots of a cubic polynomial, how do I get the third one? If you recall way back, one of the first videos, we had concluded the following. So recall that the sum of the roots of a cubic polynomial of the form ax cubed plus bx squared plus cx plus d equals, what does it equal? Minus b over a. Okay, in one of the first videos in this class, we proved such a relationship, that if you take a cubic polynomial and you add all its roots, you get minus b, this coefficient, over that coefficient. So that should actually help us a lot here. I still want to keep some of these calculations, so maybe, what do I want to erase? All right, I'm just gonna stick in the answer here. So I get that xp plus xq plus xr, these are the x coordinates of p, q, and r, these are the roots of f of x, is equal to minus b, that's this, so it's lambda squared minus a. I negated it, right? That's why I wrote it as lambda squared minus a instead of a minus lambda squared. Oh, over 1. So that's just that. Okay, I can now erase that. So I get the sum of the roots. So from this, we get that xr, which is the same as xp plus q, right? That's this equation, is equal to lambda squared minus a minus xp minus xq. Here's our first formula for the x-coordinate of this sum. You see, it's not just simply adding the x-coordinates of p and q, it's actually a more complicated formula. How do I get the y-coordinate? Well, that's easy, right? Once you have the x-coordinate, so you know that y lies on that same line. So I have that y, and yr is equal to lambda xr plus mu. So yp plus q, let me just actually write it already as a formula, There's not much to compute. So yp plus q is equal to negative yr. So it's equal to negative of that. Negative lambda xr, which is the same as xp plus q, minus mu. Okay, so that's the formula for the y coefficient, for the y coordinate of the sum. So if you had an actual equation of a curve, so that means you have a, b, and c, and you take 2 points on the curve, then you can compute the x-coordinate of the sum. It's just compute the slope of the line. That's how you compute it. Minus a minus xp minus xq. And for the y-coordinate, you just do minus that slope times whatever you got here minus mu. Oh, maybe we should also say what mu is, right? That's not a complete answer yet. So what is mu? How do you get mu? Well, look, r is not the only point that lies on that line. P also lies on that line. So I also know that yp is equal to lambda xp plus mu. Because, so sp lies on L, we get this. And from here we can compute mu. So mu is equal to yp minus lambda xp. Okay, so we get the final formula for yp plus q. That is minus lambda xp plus q minus mu, so minus yp plus lambda xp. Minus lambda xp plus q minus mu. I'll just erase the box around it because that's not the final formula. Okay, so we have these coordinates for when the points are actually different points. What if they are the same point? Well, does anything change really? So let's say I'm trying to take a point P and do twice P. Now I don't want to use this point here because that's kind of, so I'm going to make a new picture because that point wouldn't fit into my picture. I mean, the sum wouldn't fit in my picture. I'm just going to pick a better point that fits into the picture, x, y. Okay, and now we do this. So we take a point P somewhere like here. Okay, and we want to find 2P. So what do? We draw a tangent line. It intersects it. It intersects the curve at another point R. And we drop it down here. And that's 2P. So its coordinates are x 2P, y 2P. Let's see what's different in this case when we do the calculations. Okay, so that's still a line L. And I would still write it in this form. Right? It's still of the form lambda x plus mu because the point does not lie on the x coordinate, so the line is not vertical, right? That was one of our assumptions. So this is now case. So now P is equal to Q. None of them, so not equal to infinity. And the y coordinate is not 0. Which means the point doesn't lie there, so the tangent line is not vertical. So the tangent line has a well-defined form L equal to y equals lambda x plus mu. Okay, so still the same thing. And this formula still holds, but the formula for the slope is different. How do you get the slope of the line? Well, this is a tangent line, so how do you get a slope of a tangent line to a curve? You compute the derivative. So lambda will be dy over dx at the point at the point P. And just write it like this. It's dy over dx at the point P. Okay, so let's compute dy over dx. Well, this is a curve like that, so we need to use implicit differentiation here. That's not a big deal, we can do it. So we compute the derivative of both sides, d over dx. What do we get? We get 2y dy over dx is equal to 3x squared plus 2ax plus b. Okay? So from this we get the formula for the slope. That's lambda dy over dx is equal to 3x squared plus 2ax plus b divided by 2y. Okay? And now because we want it at P, so this is where at the point P, so this is xp, and yp. And look, I mean, the yp not equal to 0 actually comes in handy here, right? The derivative is the slope is well defined. Okay, what then? Well, then I do exactly the same thing that we did a moment ago, right? So I just do that. Still y is equal to lambda x plus mu. It's just lambda has a different formula. So after squaring, you get that. You equate these two. You reorganize the terms so that everything is on one side. And you still get exactly the same formula. You get exactly that. So after doing the same steps, you get that x to p is equal to lambda squared minus a minus, okay, xp and xq are now the same because p and q is the same point, so it's minus 2xp. The thing is that it's a different lambda, right? This lambda here is that lambda. And what about y to p? It's exactly the same. It's like this, minus lambda x to p minus yp minus lambda xp. So exactly the same formula, except that it's a different lambda. All right, so here let me just box that. I just want you to notice that it's actually not two different formulas, because if I just put in p equal to q into this formula, I get that formula. And same here, if I just put p equal to q here, in this formula, I get that formula. The only thing that you have to be careful is that it's the lambda is different. When the 2 points are different, then lambda is yq minus yp divided by xq minus xp. When the 2 points are the same, it's this more complicated lambda. Okay, just to be sure, I want to just put back the other lambda. So this is this lambda, right? And I want to put back the other lambda here to, so here the lambda was equal to yp minus yq doesn't matter, right? Which order I write it. Yq minus yp over xq minus xp. Okay, so that's this lambda here. All right, so we have these two cases. Let me divide the board here. In this case, down here is for p equal to q. And this case here, all this is for p not equal to q. And this other, so not equal to infinity, and xp not equal to xq. Okay, so that these two cases here, two general cases that we covered. And I want to finish this lecture with one important observation. It's like very important observation. One reason, I mean, these formulas are useful anyway because we're going to be computing these sums on these curves. But suppose now, before I write this down, I don't want to, maybe I can just write this down here and erase this picture. So a very important theorem, which we essentially just already proved. So let me just write down the statement here, theorem. If A, B, and C are rationals, okay, so these coefficients that were supposed to be real, suppose they're actually rational numbers. And suppose, and P and Q both have rational coordinates, rational x and y coordinates. Okay, so these are rational points on these curves. That means they have both of their coordinates, xp, yp, and xq, yq are rational numbers. Then look at the coordinates of xpq, for example. There is lambda, but lambda is this. xp, xq, yp, and yq are all rational. So when you do this, lambda is also rational. A is rational. xp is rational, xq is rational. Then xp plus q is also rational. What about yp plus q? Minus lambda, that's that lambda, still rational, times xp plus q, we just said it was rational, minus yp, which is rational, lambda rational, xp rational, so that is also rational. Let's try this here. Well, here everything is the same except the lambda is different, right? Lambda is given by this, but xp is rational, a is rational, again xp, b is rational, and yp is rational, so lambda is also rational in that case. Then the coordinates of xp plus q are both rational. It doesn't matter whether p is equal to q or not. And this is an incredibly important statement because you will see how difficult in general it is to produce points on curves that have both rational coordinates.